but we got 0 over 0. Do you remember this? We started to talk about this yesterday. You're still going to try direct evaluation to start every problem because you don't want to do all this work and find out, shoot, like I could have just plugged in 3 and been done with it. But on this one, if you do plug in 3, you're going to get 9 minus 3 minus 6, which is 0 up top, and 3 squared minus 9 is 0 on the bottom. That is not undefined. Any other number over 0 does not exist. This is just, it's too early to tell. We have to do some simplifying and manipulating. And that simplifying for today is all going to be factoring. So we would simplify the top by factoring into x minus 3x plus 2. And on the denominator, x minus 3x plus 3. And so here's the thing. Of course, that's going to cancel, but that's exactly what you wanted to happen because what was making the issue in the denominator was that 3, right? Plugging in a 3 to a factor of x minus 3 is what was making that 0 come up in the denominator. Now that it canceled, we can reevaluate. So this function simplified to that function. So we're going to reevaluate the limit as x approaches 3, but now on this reduced version. So now you plug in 3 and you get 5 over 6, and that's your answer. If I showed you that original function, and we've talked about this with rational graphs, but I want to reiterate it right now because it's been a while. If I show you that original function, this one, pre-factored and canceled, I get this graph. Okay? On another calculator, I'm going to type in the simplified version, x plus 2 over x plus 3. And what would you say about these two graphs? They certainly appear to be identical, right? The only thing that's not identical about them is what? One of them has a hole, right? The original one has a hole. And that hole comes from, you figured it out based on what canceled. It's at 3. Yes? So if I were on this left one is the original one. If I were to do second trace and look for the value at 3, it's going to come up blank because it isn't defined in the original version. Yes? You don't see the hole necessarily. If I do second trace on the simplified version and I look for the value at 3, it's going to give me 5, 6. Does that make sense? So for all intents and purposes, these graphs are identical, except for this one had a hole and therefore couldn't be evaluated at 3. This one no longer has that hole, so it can be evaluated at 3, and that's why we have the limit. Because, again, even though this function has a hole, it still has a limit. A limit existing is different than the function value existing. So even though this graph has a hole right here, and f of 3 does not exist, that doesn't mean that the limit of the function as we approach 3 can't exist either. Capiche? Connor? Does not exist. So if things cancel and you still get something like 5 over 0 after the fact, then your limit doesn't exist. That's not a hole. That's probably an asymptote. Faith? Nope. You only need to manipulate stuff if you get 0 over 0. Good question. Okay. Number 10, just to be sure, and I'm pretty confident it's going to happen with all of these because this is what we're learning, but if you plug in 4, you're going to get 16 minus 8, 0 over 0. Okay, so now we factor and cancel. X minus 4, x plus 2 up top. And on the denominator, we pull out an x, and we have an x minus 4. So we see that our hole is going to be at 4. which explains why the value of the function didn't exist at 4, but the limit might. So we re-plug in 4 to just x plus 2 over x, and we get 6 over 4, which is 3/2, and that's our answer. Kind of tells us where our hole was. It was at 4 comma 3/2. 4 plus 2 is 6 over 4. Are we go with that? Any questions? Okay. The factoring is just a little bit more complex. Can we just assume we're going to get 0 over 0 in here? Good, because I don't want to do the math. All right, so now just a 4-term polynomial. How do you factor a 4-term thing? Grouping. So on this one, I'm going to pull out an x squared, left with x minus 2. On the second grouping, I'm going to pull out a positive 4. I'm left with an x minus 2. So that worked. I get an x minus 2 and an x squared plus 4 for my numerator. Oh shoot, I didn't really leave myself much room for the denominator. Oh well. I'm going to pull out an x cubed. I'm left with an x minus 2. What do I pull out of this one? 1. With grouping, you never pull out nothing. You always have to pull out something. And by default, it's 1. So the x minus 2's match. So my two factors are x minus 2 and x cubed plus 1. And so the factor that cancels is the one that, of course, was problematic, right? When you plug in a 2 to a factor of x minus 2, that's what was causing the 0 over 0. So now we don't have to worry about that. And we can reevaluate. I could keep factoring if I wanted to. There's just no need. Faith, kind of to your question before. That denominator is the sum of perfect cubes. It's been a while. So we could still factor that if we needed to search for more things to cancel. But the problematic factor that was giving us 0 over 0 is gone. And now we can just plug in 2. And we get 8 over 9. $12 looks like fun. What would be your plan on 12? No, because you're going to get 0 over 0. So it's indeterminate. So we gotta play around with this more. Yeah, because if you plug in 0, you're going to get 4 squared, which is 16 minus 16, so it's a 0 up top and a 0 on the bottom. So Andrew's method is distributing, meaning squaring this out, and then simplifying the top, and then factoring the top. That's one option. Does anybody see any other option? No? All right, let's do it that way then. I'll show you when we're done. So if we square that out, we get 16 minus 8x plus x squared, minus the 16 at the end. And then that numerator is just going to boil down to x squared minus 8x all over x. So now if you factor out in the top, it's just a GCF. And your x over x, which is the problematic factor since x is approaching 0, that's what was causing the 0 over 0. So now that that's gone, reevaluate, and your answer is negative 8. Good. Oops. Okay, so that's fine. I just was curious. I'll show you what I was wondering if any of you noticed. If I do this, what am I doing? What? You don't like the parentheses and brackets? I feel like in your Algebra 2 curriculum, there was a lot of like funky factoring cases like that. What method of factoring did I use versus what you used? No. Yes. That's the difference of perfect squares. So when you have blank squared minus 16, it factors into conjugates. Something plus 4, something minus 4. 4 minus x plus 4, 4 minus x minus 4. And then from here, you would just 4 minus 4 cancels. So it's just negative x. The x cancels with the bottom. So you have a negative sign. And then this 4 minus x plus 4 is 8 minus x. Oh, that x in the bottom already canceled. And then you just plug in your 0 now. Yep. I just didn't know that, like that. So you guys, I know that's just really Algebra 1. You've just been trained for so long that if you see something squared, FOIL it out. But I mean, what's that? Yeah, I think, well, getting anything with all those parentheses gone and as a trinomial without parentheses is definitely easier for you, just based on the way you've been trained. But I didn't know if anyone saw the difference of perfect squares there. Apparently not. That's okay. That's fine. Can go either way. All right. Piecewise functions is a little bit different. Direct evaluation just does not work, okay, for most numbers or most problems, because they're almost always going to ask you about the limit as you approach the place of transition. So in this piecewise function, prior to 2, we're following this graph. After 2, we're following this graph. They're usually only going to ask you for the limit surrounding 2. And if you just plug in 2, and I'll show you the picture of this in a minute, you're probably not going to get it right, because if you just found f of 2 here, which equation would you be plugging 2 into? The first or the second, if you're plugging in 2? The second, because that's where we equal 2. If you just plug 2 in here, you're going to get 7 as your function value. Not necessarily going to be the limit value, because remember, in order for the limit to exist, it has to be the same coming from the left as it is from the right. So this particular piece is approaching 2 from which side, the left or the right? When x's are less than 2, from the left, okay? So this particular piece of our piecewise function ends with an open circle. Do you see why it's an open circle? Because why? Right, there's no or equal to sign. So this section is going to end with an open circle at 2 comma 9. 2 squared plus 5 will give you 9. The next piece is going to begin with a closed circle at 2 comma 7, we said. So one graph is ending at 2, 7. Well, ending at 2, 9, I should say, with an open circle, and that looks something like this, because we only want to see that quadratic to the left of 2. And the other one, which is a line, is starting at 2, 7, and it's a line with a positive slope of 3. So when you see that image, it's much easier to tell that as I approach from the left, I have a different number than if I'm approaching from the right. Agreed? Approaching from the left is using that first piece, which gave us a 9. Approaching from the right was using that second piece, which was a 7. And because those don't match, the overall limit does not exist. Any questions on that? You don't have to draw the picture every time, but it does help make sense of what's going on. But you really, if you're coming from the left or from the right, you have to decide. You're always plugging in 2. It's just which equation you plug in 2 for, depending on the scenario of which direction you're coming from. Oh, maybe. So on this one, if I'm approaching 1 from the left, I'm plugging in 1, but to which equation? Which one is 1 from the left? The first or the second? Right. If you're coming at it from, and if maybe a number line helps, just put this in perspective. If you're coming from the left of 1, you're coming at a number that's less than 1. That fits into category 1. So we would plug in 1 here and we would get 1, negative 1. So that one's ending with an open circlet, negative 1, 1, negative 1. But the limit is that y value, negative 1. If we're approaching 1 from the right, we can directly evaluate in the piece that addresses the right-hand side of 1, which is the second. And if I plug 1 into that, I'm going to get 2 minus 1, which is 1, and the cubed root of 1 is 1. And those don't match. Sometimes they will, but they don't here. Sometimes you might have a parabola end where the next piece, a linear, begins. If that's the case, and one ends at 2, 4, and the other one starts at 2, 4, then you're okay. The limit would just be 4. So it can and they will write them purposely so that that happens. But in both of these cases, there was a jump that happened from one function to the other. Okie doke. You have 15 minutes. Definitely do that. You have 15 minutes on the clock, so get started. Oh, there, that was already cracked. I'm just going to give you 2 those. Faith, once you get yours, can you pass? Yeah. It's like when the flight attendant's trying to count everybody on the plane and everyone by What? Can you pass that down the line, please?